Section: Introduction. In this section, we discuss the importance of quantized deep learning. Quantized deep learning has become popular for efficiently deploying deep neural networks on devices with limited resources. Traditional deep learning models use high-precision representations, which require a lot of computational resources and memory. Quantized deep learning techniques offer a solution by reducing the precision of network parameters and activations. One common technique is post-training quantization, which is easy to use but may not provide the best results. Quantization-aware training, QAT, is another approach that updates quantized weights during training, leading to higher quality results. However, QAT faces a challenge when the derivatives of quantization functions are zero or undefined. To overcome this, practitioners use approximations called gradient estimators for backpropagation. There are many gradient estimation methods available, but our research shows that the choice of gradient estimator may not have as big of an impact as previously thought. We prove that different non-zero weight gradient estimators result in similar learning processes for non-adaptive optimizers like SGD when the learning rate is small. For adaptive optimizers like ADAM, the same holds true without needing adjustments to the learning rate and weight initialization. We also demonstrate the equivalence of common gradient estimators using toy models and provide empirical evidence on small and large neural networks trained on different datasets. Our findings suggest that practitioners can focus on other aspects like weight initialization, learning rate, and optimization methods, while using a simple gradient estimator like the straight-through estimator, STE. Moving on to the background and related work, the core operation in quantization-aware training is applying a quantizer function to weights and activations to convert high-precision values into lower-precision ones. We focus on uniform quantization functions, which map continuous values to discrete representations. The choice of parameters like delta, L, and U is crucial and well-researched. We define quantization bins as sets of input values that map to a single output value, with boundary points marking the edges of these bins. The straight-through estimator, SAINT, is a popular gradient estimator that approximates the quantization function to enable weight updates during training. Piecewise linear, PWL, estimators are another type that closely mimic the quantization function but can lead to saturation if the range is poorly chosen. Researchers have developed various custom gradient estimators to address the gradient error between the actual quantization function and its approximation. These custom estimators aim to bridge the gap between the forward pass and the surrogate forward pass. Overall, the choice of gradient estimator plays a crucial role in the effectiveness of quantized deep learning models. Section Summary. In this section, we highlight the significance of quantized deep learning in efficiently deploying deep neural networks on resource-constrained devices by reducing precision in network parameters and activations. We discuss the challenges faced in quantization-aware training, QAT, due to derivatives of quantization functions being zero or non-existent, leading to the need for gradient estimators for backpropagation. Despite the emergence of various gradient estimation methods, our research demonstrates that the choice of gradient estimator is less impactful than previously thought, allowing practitioners to focus on other critical aspects like weight initialization, learning rate, and optimization methods. Section: Gradient descent terminology for QAT. In this section, we discuss gradient descent terminology for quantization-aware training. We work with a quantized model using a gradient estimator hat-Q at each step t. The gradient value is calculated as the product of the gradient of the loss function f at q, w_t, and the gradient estimator hat-Q, w_t. We denote the gradient of the loss function as nabla f_t. The weight update is determined by the learning rate eta. We introduce the notation g_t to encompass various gradient descent algorithms like SGD, ADAM, and RMS-prop. For instance, in the case of standard SGD, g_t, nabla f_t, hat-Q, w_t, eta, equals eta nabla f_t hat-Q, w_t. We classify algorithms like ADAM, RMS prop, ADA delta, and ADA max as adaptive learning rate methods, as they normalize weight updates based on past gradient values. On the other hand, algorithms like SGD and SGD with momentum are considered non-adaptive learning rate methods. To provide intuition, we set up a simulation with a single weight in a quantized model using a multi-bit quantizer with delta equals 1. The weight starts at 0.7 and is updated using gradient descent with a learning rate of 0.001. We assume a constant gradient value of -1 for illustrative purposes. We compare two models: the sweet model using the straight-through estimator and the HAT-Q model with a similar gradient estimator. By adjusting the learning rate and weight initialization, we make the two models equivalent throughout the training process in the simulation. Our example demonstrates that the model with the HAT-Q gradient estimator behaves similarly to the sweet model after applying the specified transformations. The equivalence between the models holds throughout training, even if gradients change or differ between the models. As long as the transformations are applied, both models will receive the same gradients and exhibit equivalent behavior. Section Summary. In this section, we introduce gradient descent terminology for quantization-aware training, QAT. We define the gradient value at step t as nabla f_t for a quantized model with gradient estimator, HAT-Q, and the weight update is expressed as w_t plus 1 equals w_t, eta g_t, nabla f_t, HAT-Q, w_t. By defining g_t, we can recover various gradient descent algorithms like SGD, ADAM, and RMS prop, where ADAM is an example of an adaptive learning rate algorithm. Section: Main Results. In this section, we formalize the realizations from the previous section and present our main mathematical results. We aim to address concerns about gradient error and provide theorem statements for both the SGD update rule and the ADAM update rule. The proofs and generalizations can be found in the appendices. It's important to note that all the results discussed here apply to weight quantizers, and we do not delve into activation quantizers in this study. Let's start by defining the quantized learning process and change points. In quantized learning, understanding the number of steps it takes for a weight value w_0 to reach the neighboring quantization bin, w_0 plus, or w_0, is crucial. We introduce the concept of a quantized learning process, denoted as P equals Q, HAT-Q, G_T, nabla f_t, eta, w_0, w_**, which contains all the necessary information to describe how weights evolve in a quantized model. The change point C, P, of the learning process is defined as the smallest value of t at which w_t surpasses w_* based on the weight updates via a specific equation. The change point plays a significant role as it indicates the point at which the weights transition. If two quantizers consistently yield the same change points for learning processes, then their difference is deemed insignificant for quantized deep learning purposes. We aim to demonstrate that the choice of gradient estimator has minimal impact on the change points of a quantized learning process. We introduce the concept of cyclical gradient estimators, where a gradient estimator, HAT-Q for a uniform quantizer Q, is considered cyclical if it remains the same within each finite-length quantization bin. Most multi-bit gradient estimators proposed in literature are cyclical, and binary gradient estimators are inherently cyclical due to their lack of finite quantization bins. Two key definitions, alpha and m, are introduced to facilitate the learning rate update and weight initialization update required to mimic the behavior of a positive gradient estimator, HAT-Q, using only the straight-through estimator, STE. The main results are presented through theorem statements for both the SGD and ADAM update rules, showcasing that a positive gradient estimator, HAT-Q, can be replaced by the suite after appropriate adjustments. The theorems provide conditions under which this replacement is valid, emphasizing the robustness of the STE in quantized learning processes. Section Summary. In this section, we formalize the realizations of the previous section and present our main mathematical results regarding the SGD and atom update rules, demonstrating that concerns about gradient error are largely unfounded. We introduce the concept of quantized learning processes and change points, defining them as essential components for studying the evolution of weights in a quantized model. Our theorems establish that adjusting the learning rate and weight initialization in a quantized learning process allows a positive gradient estimator to be replaced by the straight-through estimator, SAINT, simplifying the optimization process. Section. On the assumptions of theorems 5.1 and 5.2. In this section, we will explain the assumptions behind theorems 5.1 and 5.2. These theorems rely on specific conditions related to the gradient estimator hat-Q and the gradient updates G_T. Our aim is to clarify these assumptions to address any doubts and ensure that readers have a solid understanding of the basis of our work. Some assumptions are rarely violated. The upper limit on hat-Q in the assumption is quite lenient. Gradient estimators with unbounded derivatives could lead to training instability and are not commonly used in practice. The constraint on hat-Q, W, for W in the range W_0, W_0+, in the assumptions is seldom breached. Similarly, the upper bound on the gradient steps in the assumption is valid in almost all practical scenarios. Breaking this bound would require creating an infinitely increasing sequence of gradient updates, which is not relevant in real-world situations. Certain assumptions are debatable. The lower limit on hat-Q in the assumptions is frequently exceeded in practice. We can adjust our results to accommodate this and provide further details in the appendix. Additionally, the lower bounds on gradient steps in the assumptions may be more contentious. These assumptions ensure that the weight updates have the same sign, are non-negative, and are non-zero. We have valid reasons for wanting these properties. The choice of same-signed weights is mainly for simplicity. If weights move in different directions, determining the first boundary crossing becomes more complex. Although occasional changes in weight update direction do not impact our main result significantly, there could be cases where differences arise due to rapidly oscillating weights within a quantization bin. We also discuss the choice of non-negative weights and the assumption of non-zero weight updates. These assumptions are crucial for comparing the effects of different models. We illustrate our main results through experiments on practical models. By comparing models using hat-Q and the STE, we show that they train similarly, with differences diminishing as the learning rate decreases. Applying weight reinitialization as per theorem is essential for achieving these results. We utilize two models: a simple three-layer quantized convolutional architecture for image classification on the MNIST dataset and ResNet 50 on the ILSVRC 2012 ImageNet dataset. Various optimization techniques are employed, including SGD with momentum and atom. For all experiments, we follow specific optimization strategies and learning rate schedules tailored to each model. Our focus is on demonstrating the effectiveness of our approach on real-world models and datasets. Section Summary. In this section, we clarify the assumptions underlying theorems 5.1 and 5.2, which are crucial for our work. We discuss the infrequently violated assumptions regarding the gradient estimator and updates, as well as the arguable assumptions related to the lower bounds on the gradient steps. Additionally, we present experimental results demonstrating the effectiveness of our approach on practical models, showcasing the similarity in training between models using different gradient estimators. Section. Metrics. In this section, we utilize a variety of metrics to establish point A. These metrics compare data from the sweep model to data from the hat-Q model. Along with these metrics, we also present validation accuracy for all models. Firstly, we look at compressed change point sequence agreement, where we track change points and their quantized values for each weight in both models. Due to weight oscillation around quantization boundaries, many weights end up having the same change points after compressing pure oscillation subsequences. We then report the proportion of compressed change point sequences that match, known as compressed CPS agreement. Next, we examine quantized weight agreement, where we calculate and compare the complete set of quantized weights at the end of training for both models. We report the proportion of quantized weights that are the same in both models. We also consider latent weight alignment error, where we compute the absolute difference between weight values for the entire model of each pair of models. This difference is normalized by the total distance traveled by all weights. Moving on to the results for the MNIST dataset, we observe minimal differences in training accuracy between the HAT-Q and SWEET models. The standard training metrics for both models using SGD plus momentum and atom are detailed in tables, showing similar train and test metrics. This suggests that replacing HAT-Q with the SWEET has minimal impact after appropriate weight initialization and learning rate adjustments. Furthermore, we provide metrics for points A, B, and C for both default SGD and atom models. Point A is confirmed through comparisons labeled as baseline, LR tweak, and scale down. Point B is validated by observing diminishing differences when the learning rate is decreased. Point C is verified by comparing alignment measurements between the HAT-Q model and an unadjusted SWEET model. For the ImageNet dataset, we conduct similar comparisons as for MNIST, excluding the change point metric due to memory constraints. Despite this, points A and B are validated for ResNet 50 on ImageNet. In terms of implications, we discuss the impact of our work on existing literature and future practices. For practitioners, the message is straightforward based on the optimization strategy used. For researchers, we hope this work inspires further exploration into updating quantized model parameters through methods distinct from gradient estimators.